Did you know there are creatures on Earth that actually live in acid? They're microbes called acidophiles, and they thrive in places like volcanic springs and mine drainage sites. These environments are so acidic they'd burn your skin. There are also thermophiles. They survive in places where temperatures are hot enough to cook your dinner or melt your sneakers. For example, you might find them near hot springs, like this one at Yellowstone, or perhaps near deep sea vents where scalding water blasts out of the sea floor. Scientists have even found bacteria living deep underground, sealed inside rock for millions of years without sunlight or oxygen. They survive by feeding on the minerals around them. These are extremophiles, life forms that break all the rules of where we once thought life could exist on Earth. And they've made scientists rethink where life might exist beyond Earth, too. Because if life can survive in boiling acid or deep underground, maybe it can survive on a frozen moon like Europa, or in the salty soil of Mars. Today we're diving into one of the biggest mysteries in science. Is there life beyond Earth? What kinds of places might support it? And how do we actually search for it? Before we go alien hunting, let's think. We've talked about this before. Do you remember the key ingredients for life? Hit pause and see if you can list them. What makes a planet or moon a good candidate for life? Let's see how many requirements you remembered. There are a few big clues that scientists look for when deciding if a place might support life. First up, liquid water. Life as we know it needs a liquid, something to help chemical reactions happen and move nutrients around. On Earth, that liquid is water. Even the weirdest extremophiles, like the ones living in hot springs or beneath ice, still need liquid water to survive. That's why Mars gets so much attention in our search for life. Evidence shows it once had lakes and rivers, and there may still be salty water underground. Now, it's possible that life elsewhere could use a different liquid, like methane or ammonia, but since water works so well here, it's our starting point when looking for life beyond Earth. Our next clue? Organic molecules. These are life's building blocks, simple combinations of carbon, hydrogen, and oxygen that form things like proteins, DNA, and cells. Finding organic molecules doesn't prove there's life, but it's promising. And yeah, Mars has these molecules too. Finally, we need the right environment. This usually means being in the habitable zone, the not too hot, not too cold area around a star where liquid water could exist. But it also means having energy sources like sunlight or chemical reactions, and protection from things like deadly radiation. Put it all together and you've got a checklist scientists can use to evaluate planets and moons both inside and outside our solar system. If a place has water, organic molecules, and a stable environment, it goes straight to the top of the list to explore further. Let's put that habitability checklist to the test. Imagine scientists discovered a new planet orbiting a nearby star. Here's what they know. It's slightly smaller than Earth. It orbits in the star's habitable zone. There are signs of ice-covered oceans on the surface. The atmosphere contains carbon dioxide, hydrogen, and a hint of methane. There are signs of possible underwater volcanic activity. So what do you think? Is this planet a good candidate for life? Hit pause, think it through, and make your call. This planet checks a lot of the boxes. It's in the right zone for liquid water, and even though the oceans are frozen on the surface, volcanic activity could create warm spots underneath. Just like on Jupiter's moon, Europa. The atmosphere includes gases like methane, which could be produced by life or by geological activity. Either way, it's intriguing. No one's calling it alien paradise just yet, but a planet like this one would definitely grab the attention of scientists. So, how do we find places like this? One of the most important tools in our search for life are planetary probes. But searching for life requires probes that do more than snap a picture. A key strategy is finding biosignatures, substances in the environment that might suggest life is or was there. One example is methane. On Earth, most methane in the atmosphere is produced by living organisms, mainly microbes. It can also come from volcanic activity, but if we detect methane on a planet like Mars, scientists want to know how it's being made and if something alive could be behind it. Oxygen is another big clue. Here, planets and algae constantly release oxygen through photosynthesis. But oxygen reacts with other chemicals and processes such as rusting, so it doesn't stick around in the atmosphere forever. If a planet has a steady supply of oxygen, something might be actively making it. Then there's phosphine, a gas that, on Earth, is linked to microbial life, specifically extremophiles, that survive in oxygen-poor environments. A few years ago, scientists thought they found it in Venus's atmosphere. That's still debated, but if it turns out to be true, it raises some pretty wild possibilities. Each of these molecules might have a non-living explanation, but if we detect the right mix in the right environment, it could be a strong hint that life is, or once was, there. Probes like the Europa Clipper were designed to look for these biosignatures. Europa is one of Jupiter's moons. It's covered in ice, but underneath that frozen shell is a massive ocean, possibly twice the volume of all the water on Earth. And at the bottom of that ocean, there might be hydrothermal vents, hot cracks in the seafloor where heat and minerals pour out from inside the moon. Here on Earth, those same kinds of vents are home to thriving communities of extremophiles. If something similar exists on Europa, it could be one of the best places in the solar system to find life. The Europa Clipper won't land, but it will fly through water plumes that shoot out of Europa's surface. Its instruments are designed to detect signs of life, like salts, organic molecules, or temperature shifts that could point to active hydrothermal vents below the ice. So whether we're sniffing methane on Mars, scanning water plumes on Europa, or analyzing gases in the atmosphere of some other planet or moon, the search for life is all about spotting these tiny traces. Let's say we find something. Maybe it's a chemical signature geology can't explain, a frozen microbe under Martian ice, or a hint of something swimming deep below Europa's crust. What then? It would be one of the biggest scientific discoveries in human history. It would mean life isn't an occurrence so rare that it only happened on Earth. It happened in other parts of the universe too. New questions would be raised very quickly, like, what kind of life is it? Is it similar to us? How did it survive? What else can we learn from it? Plus, big discoveries come with big responsibilities. If we find life, we have to be careful. There are ethical questions we need to face. Should we keep exploring or back away slowly and pretend we didn't see anything? How do we study alien life without harming it or spreading tiny Earth organisms like bacteria by accident? These are questions scientists already take seriously. That's why space missions follow strict rules to avoid contamination both ways. We don't want to damage alien ecosystems, and we don't want to bring back something we don't understand. So does life exist anywhere else in the universe? We don't know for certain, but astronomers are determined to keep searching for clues. Until next time, stay curious and don't stop asking what else might be out there.
Hey, hey.